Right, well, as Jorge says, let's bring on Liz, the FIA's Circuit Safety and Commission Coordinator, who's going to share her expertise on circuit licence grades and the circuit homologation process. So, Liz, over to you.
Thanks, Tom. And thanks to everybody who's signed up for this session online. My name is Liz. I've been working with the Circuit Safety Group for some time now, and I manage mostly the homologation and grading of circuits. So with that, we have a slide with the speakers. Here's the agenda of the presentation, which will give you a brief overview about what topics we're going to be getting into in greater detail later today, starting with circuit license grade and the circuit homologation process. Across the world, we have more than 300 currently licensed circuits. Of these, more than half of them are currently located in Europe. But as you can see, we have a strong presence in other areas of the world that's growing exponentially. We can see the progress that we've made over the years by the fact that there were 200 FIA licensed circuits in 2015, and now 10 years later, we have more than 320. In the infographic in front of you, the different grades of circuits are represented by different colors of circuit outline. The different grades of circuits are mostly determined by the performance of the cars that will be racing on them. This begins with the pinnacle of our FIA circuit grading pyramid with FIA Grade 1 circuit, which is destined for use by cars which have a weight-power ratio of less than 1 kilo per horsepower. Currently, this is Formula One. While we only have 24 races on the Formula One calendar, we have more than 50 homologated circuits to the same stringent Grade 1 safety standards. Moving down the pyramid, we have Grade 2 licenses, which are for cars with a weight-power ratio between 1 and 2 kilos per horsepower, and decreasing down through Grades 3 and 4. For the Grade 5 license, which I'll speak a bit more about later, we've decoupled it from the vehicle performance. Grade 6 licenses are for all off-road competitions, so that's autocross, rallycross, and ice racing championships. Finally, the Circuit Safety Department works closely with the ASNs and other sanctioning bodies to validate the licenses of drag strips and land speed record attempt venues. A new grade of license that was approved at the end of 2024 and is in fact so new that it hasn't made it to the previous slide is a grade FE license. And this is a dedicated license that we've decided to implement for all circuits that will be hosting a round of the FIA Formula E World Championship. This is really due to the specific nature of the vehicles, the rapid evolution of the cars, as well as the specific requirements of the primarily non-permanent circuits. The other grade of license that I mentioned we're going to touch further on is the Grade 5 license. This is also relatively new in our circuit ecosystem. It was implemented in 2022 and is an entry-level grade of circuit for a circuit who may not be quite ready to apply for a full FIA homologation, but still is interested in improving the safety and learning the steps to take along the circuit safety ladder. There's a simplified application procedure with a simplified list of documents, and a basic safety simulation study is carried out on the circuit to give recommendations not only for how to improve safety in an immediate and cost-effective way, but also what steps could be taken for the future. This license is not intended for international competition, but is a great first step towards a circuit that may be interested in obtaining that in the future. With that in mind, the fee that the FIA charges for the Grade 5 license is a very low one and only covers the FIA administrative costs. The circuit inspections that are carried out as part of the Grade 5 licensing procedure are done in grouped inspections and are not charged to the circuit. If a circuit that has obtained an FIA Grade 5 license wishes further to submit a full homologation dossier for a higher grade of circuit, the price of the FIA Grade 5 homologation can be deducted from any further circuit license that they may request. That brings into the next part of the presentation, which is going over the circuit homologation process and how a new circuit can begin to achieve FIA homologated status. There are 8 basic steps, starting with the compilation of the homologation dossier that comprises different documents that are necessary for the FIA to be able to assess the suitability and safety of the circuit. These documents are compiled and submitted via the ASN of the country. So this is an important step to note that at every point the ASN is involved and included, and we exclusively communicate through the ASN to make sure that they are kept up to date about the process of the works on the circuit and the homologation status. Once all the documents have been received, our talented colleagues in the FIA Circuit Safety Department carry out an initial analysis to ensure that the circuit can comply with FIA homologation in principle. Furthermore, they carried out a detailed safety simulation using our bespoke simulation and modeling tools, which my colleague Stavros will be speaking about later. The recommendations that have been gathered from this detailed safety study are submitted to the Circuits Commission and the Circuits Project Working Group, which is comprised of worldwide experts in circuit construction, homologation, and race operation. This commission will also delegate an inspector chosen based on the inspector's experience, areas of interest, availability, as well as geographical location. Once the inspector has made an initial visit to the circuit, he will report back with a full report detailing the status of the works and any improvements to be made. Up to 3 circuit inspections can be carried out in a different loop until the circuit inspector is satisfied with the works and the status of the circuit. At that point, the FIA circuit safety team compiles all the information into a comprehensive dossier and submits it to the FIA president for his signature. The most important part of the circuit homologation process is the circuit dossier that is submitted by the ASN to the FIA. And the most important document included in the circuit dossier is the AutoCAD plan of the circuit. This is the detailed plan of the circuit showing the layout, the location, all the safety installations, as well as design details of the curbs, the energy absorbing barriers, and further information that we assess as part of the safety of the circuit, such as the elevation, the drainage information, marshal post information, light panel locations, and medical center information. This is the reference document that we use to assess the safety of the circuit throughout the entire inspection and licensing process. The inspection process, which is carried out after the FIA has conducted a preliminary safety study, is heavily reliant on the FIA circuit inspector, which we have the chance to be hearing from several of later in this seminar. The circuit will make between 1 and 3 inspections during the construction of the circuit. Typically, after each visit, a circuit inspection report is prepared and presented to the FIA Circuit Safety Department, who reviews it, approves it, and shares it with the ASN and the circuit, ensuring that all the stakeholders are kept up to date about the construction timeline of the circuit. A final inspection will take place immediately prior to the first international competition. At that point, the license will have been signed and issued to the circuit with the approval of the president. The timeline for the inspection and the homologation of the circuits differs between permanent circuits and non-permanent circuits, in that permanent circuits complete the work much faster than non-permanent circuits. The inspections for a new permanent circuit should take place 60 days before the proposed date of the first international competition, or 90 days in the case of Formula One events. The final inspection, after which time no changes should be made to the circuit, takes place 30 days before the date of the first international competition or 60 days for Formula One. And before the first international competition, there will always be a pre-event check inspection the day before or even hours before the start of the competition. This timeline is different for non-permanent circuits due to the fact that their construction is finished sometimes only days or hours before the event begins. In this case, we ask for a lot more communication and reassurance from the ASNs and from the circuit constructors that the dossiers are received well in advance so that we have enough time to do the analysis and comments necessary before issuing the license. 60 days before the event, at least the track surface and major safety installations should be in place. And 30 days before the event, we request that the ASN coordinate with the circuit and confirm to us in writing that the circuit will be built according to the latest approved reference plan and that no further changes are planned. The final inspection for a non-permanent circuit happens as soon as the circuit has been built. And our inspector is always on place, on site to deal with any last-minute changes, which Scott will tell us about later in the presentation. As the final step of the homologation process, we have in front of us an FIA circuit license showing the main important features of the circuit, such as the length, the layout, direction, the date of the definitive inspection, which means the date of the inspection at which the circuit was deemed to be acceptable for homologation, as well as the circuit reference plan. The circuit reference plan as figures on the FIA license is the most important part of our process because it is that reference plan that the circuit must remain in conformity with. If barriers are moved on the circuit, it means that the circuit is no longer in conformity with the reference plan and the validity is no longer current. For this reason, it's very important that we have a documented chain of any repairs or modifications that have been done at or immediately before an international race weekend. These changes can be made in the event of accidents, in the event of damage caused to the circuit, and must always be approved by the race director or the clerk of the course. And the race director or the clerk of the course must be convinced that these changes are being made in the best interest of maintaining safety. The important step is that these modifications should be sent to the FIA at the earliest possible opportunity so that we're aware of the changes that have been made and can reflect them in the updated reference plan on a new license. Thank you very much.
Liz, thank you very much. I had no idea there were so many grades of circuit and I didn't know the homologation process until you explained it. Couple of things. Sapia from Motorsport Singapore, hello again, by the way, has got in touch saying, how do we grade a street circuit?
Street circuits are subject to the same safety criteria as a permanent circuit. We don't have allowances made for the fact that it is a non-permanent circuit. There are, of course, different construction methods that are taken into place, but a grade 1 non-permanent circuit and a grade 1 permanent circuit have the same levels of safety.
And one from me, the FE Formula E grade of license. I know you said it's very new, but how different is it to, let's say, a grade 1?
The license, well, it would be more equivalent to a grade 2 or a grade 3 based on the performance of the Formula E cars. But the main change is that having the Formula E license decoupled from the weight-power ratio and the performance of the cars enabled us to be more agile in able to move the circuit grades with the performance of the cars. Formula E is a category that is rapidly evolving, and the performance of their cars is changing from year to year. Our current licenses are valid for a period of 3 years. With the changes to the generations of Formula E cars, their power is increasing, meaning that what may have been suitable on a grade 3 circuit 2 years ago may need to be grade 2 in the future. And this enables us to really tailor the vehicle models that we use for simulations to that license rather than having to change the grade as the cars progress.
Okay, thank you. Thank you very much for explaining that. Thank you for a great presentation. Let's move on next to the FIA's Circuit Safety Manager, Stavros Touse, who's going to be joining us via Zoom. And Stavros, well, you've got various topics to talk to us about, so over to you, Stavros.
Thank you very much, Tom, and thanks to Liz for the clear presentation on the homologation process. For myself, hello to all of the viewers. So I want to start and following Liz's introduction to the homologation process. I would like to concentrate a bit more on the safety study itself and what that entails. So starting with, I would like to go to the, to the circuit safety analysis system. So very quickly, the safety study is responsible for implementing the appropriate extent of runoff areas, the position and the specification of the energy absorbing devices across all the FIA homologated circuits. So for us to be able to accurately predict these areas, we have developed the so-called CSAS software, which is short for Circuit Safety Analysis System. So this basically this tool, this software has enabled us to be able to confidently create and generate data that we can clearly communicate to our inspectors. So we provide them with data-driven information. So when they're on, as Liz explained, when they do the inspection themselves and they're on the ground, they have a report or a dossier or information, enough information for them to do the job as effectively as possible. A bit of a background in that respect. So from the safety point of view, the size of the deceleration areas and the position and specification of the barriers is a major concern for us. And as a general principle, we do recommend that when the impact angle or a potential impact angle is very low, then we accept to have the first line of protection or the guardrails close to the track edge. But if the impact angle is quite high, then we recommend to have an appropriate runoff area big enough to decelerate the car enough and combine that with a proper energy absorbing device to work effectively. So the CSS capabilities, a bit more into what the software can do. It provides us with a lap time simulation. It has the ability to, and we are able to modify the vehicle models and the setups. So we can fairly easily and quickly, for example, if you've got a new generation of cars coming up in the next 3-4 years, we fairly quickly can and input this vehicle model to our software and understand how that affects circuits. An example is, for example, the F1 2026 are doing major specification changes into the cars, so we can fairly quickly get these performance levels of the cars and understand if any circuits with grade 1 hosting Formula 1 would require any safety modifications. The software is able to take into account all the 3D information that we receive from the designers, or as Liz explained, the dossier itself contains the AutoCAD plan, which contains 3D information. So the software does calculate the speeds and the deceleration escape lines based on that information. So when you have differential levels between track edge and runoff, that is being taken into account and provides us with a lot better data. It provides, as mentioned, the escape lines and the potential impact speeds if these escape lines come into contact with a first line of protection, a barrier. And we are very, with the software, we are very able to very quickly modify sections of the circuit to understand how that impacts the safety itself. So, for example, if you have a barrier configuration which we think is not optimized for safety, we can fairly quickly modify that and see live the result of that impact, and therefore understand if it's improved it or not. And lastly, it gives us the ability, it's a very user-friendly to be able to create reports for the inspectors. So once we have done that calculation of the speeds of the escape lines and the impact speeds, it can fairly create compile this information into a report like a document, and we can provide that to the inspectors to do the job more effectively. So the next one is the methodology, just very quickly how the software works, what it does on the background, and how it gives us that information. It's firstly, it calculates the racing line automatically, or we are able to import vehicle-based racing lines based on the lat and long. And from the racing line, it calculates the speed based on the acceleration value, so based on the performance levels of the car that we have given with the quasi-static vehicle model. And once we have the speeds on the racing line itself, it can calculate the escape lines that you saw on the earlier slides based on the deceleration rates that we have extracted from accident data recorders. So a research team is helping with that. They collect tons of information based on accident recorders, and therefore they're able to extract an average of deceleration rates based from worst case to base case, and gives us a very good estimation of what to expect if a car loses control on the racing line. And that gives us, from that point, it gives us a tangential line, an understanding of how far it needs until it stops into a safe speed. So if the escape lines come into contact with the barriers, then the software calculates also the perpendicular component of that impact speed. And this is how we are able to understand what energy absorbing devices on that area of the incident would be required. So for us, the first option is to have a big runoff area that you barely need any energy absorbing devices, but we understand that's not always the case, and quite a lot of circuits are space restricted. So if that's the case, we kind of trying to do an analysis based on both trying to modify the runoff a bit, but also defining the appropriate energy absorbing device required for such an incident. So next, very quickly again, that shows a quick example of one of the projects, and is a calculation of the escape lines, and shows if the vehicle did not come into contact with any of the barriers, this is kind of the space that would be required to have on the runoff areas. But that's not, excuse me, that's not always the case. And therefore, it also provides us with the impact speeds, which gives us the information that we need to provide recommendations as to what is acceptable for each section of the circuit to be improved in terms of energy absorbing devices. So this is kind of a quick overview of the analysis and the study we do internally. And once we have this information, as I said, we compile everything into a report-like document, all of our recommendations. And we go throughout that process where we do the initial study ourselves internally. Through our experience, we do the risk recommendations. We send this feedback to the appointed inspector. The appointed inspector gets back to us if they've got any further comments to make, or if they think that some of the comments could be amended or changed. And if between ourselves and the inspector are happy with what we have written, this report goes out to the ASN for further issuing it to the circuit for the implementation. So that's a very quick overview, and this is kind of the process of the safety study itself. Moving on, I would like fairly quickly to give you a bit of a understanding and a bit of a comparison of how the data and the safety study and the simulation data we get, how it correlates with actual accidents. I have compiled 2 incidents from Formula One events that I would like to give you an example of, and how this ADR data correlates to what we predict with our tool. So fairly quickly, that's Leclerc in Monza. Okay, so I don't want to spend too much time on the video. You've probably seen that yourselves before in the past. And just to give you an understanding of what's happened, Leclerc had a bit of a snap oversteer on that corner, tried to correct the car. The car just spit him out into the runoff area, taking him tangential straight into the runoff gravel. As they said, probably the brakes were off, and then head off straight into the tire body itself. Now, we have collected the ADR data from the physical accident itself, and we had a loss of control speed of 210 kph and an impact speed of 155 kph and an impact angle of 33 degrees. Now, comparing those two together with the SIS software, we have found that the trajectory is pretty much what we would expect and what we have predicted ourselves. And a quick comparison is that the resultant perpendicular impact of the actual accident was 84 kph, while we predict 89, which is a very good estimation. And we always like from our tools to, I would say, over-predict in a way that gives us a bit of a lean room to provide more safety into the circuit. In a way, we always have that buffer of more margin on our simulations to have higher speeds because of what you can see here. The accidents can be unpredictable, and therefore having a bit of a buffer, it works quite well. So yeah, so the comparison is only 4 to 5 kph between the physical and the simulated world. So the next example is an accident by Max Verstappen in Silverstone when they were fighting between Lewis Hamilton and himself.
Keep the delta positive.
Okay, again, I don't want to spend too much time. Luckily, the driver was okay. No one was hurt, which is always what we want to see. No one being hurt on such incidents. But unfortunately, we cannot always stop such incidents. Very quickly, again, the two cars came in contact. The car of Max Verstappen therefore lost control, went tangentially to the racing line straight into the barriers. The loss of control speed was as high as 285 kph. The impact speed itself was 156 kph, and the impact angle was roughly 125 degrees. Now, when we compare that with the CSIS, we again took the position where the loss of control of the physical car was. We put that into our tool to understand which escape line that is, and we took the same point. We therefore calculated the impact speed from the CSIS tool to be 139 when the resultant, the perpendicular component of the impact speed was 135 for the physical accident. And again, on this example, it gives us the confidence that the tool that the information that we provide or that we get out of the tool is quite close to what we would expect on a real-world accident. So, okay, that was the bit for the comparison between physical and simulation. But the last bit for myself, and being conscious of time, is is the FIA circuit guidelines. Just give you a bit of an overview of what the circuit guidelines are and what they are meant for. So this document is provided by ourselves to all the SNs and parties that are involved on the design and construction of circuits for competitions registered into the international sporting calendar. It is a confidential document and must not be reproduced or disclosed without our written permission. It's used by the Circuits Commission and the circuit inspectors to assess new circuits, newly modified circuits, or existing courses. So this is almost like the Holy Bible that they hold when they do circuit inspections to understand if everything complies as per the guidelines or regulations. This document might be distributed to third parties with reference to all applicable FIA and ASN requirements, local laws and local regulations. It is updated every year and it takes into account conclusions of the latest research projects and best practices from each year. A quick overview as well again into the circuit safety measures and what we refer to as the first line of protection, second line of protection, and the runoff areas. The runoff area or deceleration area is comprised of an asphalt, a gravel bed, leading into the first line of protection, leading into the first line of protection, which is usually the stopping barriers, can be walls or guardrails, and is combined with energy absorbing barrier, such as a tire barrier or a tech pro. And behind the first line of protection, we have the second line of protection, which is usually a reinforced debris fence in front of grandstands and marshals to protect them from any potential incoming debris. Now, within the guidelines, you find all the information you need about the first line of protection, second line of protection, how to define runoff area, best practices, etc. An example here is the concrete wall and what are the specificities of such a concrete wall, how it should be constructed. Like for example, if the facing of the concrete barrier should be perpendicular to the face of the circuit, and it should be constructed with 1 ton per meter. The minimum length or recommended length is 4 meters, but shorter length concrete barriers could be allowed on tight corners or inside of a corner, where we understand that the radii could be quite tight, and therefore you would need shorter blocks. And of course, the connections of these barriers need to be with end joints and should be suitably reinforced to compensate for any discontinuities. Next one is the guardrails. Again, we can get all the information we need for the guardrails and how these are constructed, which creates the first line of protection. The connection of the guardrail and the surface presented into the oncoming cars should be a continuous surface because the sections of the guardrails are overlapped on top of each other. So it needs to be consecutive sections of the guardrail and they must not have any discontinuity between them. And the overlapping sections, they should always go with the direction of the cars or the direction of the circuit and never in the opposite direction, because that way it could cause almost like an edge lag type that if a car slides into it, could peel off the section of the guardrail. Now, the metal supports are usually U-section with reinforced angles, and they're set into the ground with a minimum depth of 120 centimeters. And for newly built circuits, licensed from 2019 onwards, we only accept metal supports and no wooden supports are allowed anymore. For existing circuits, of course, that do have wooden supports as for the first line of protection, a program of works is established to replace them to an acceptable steel metal post instead. And the spacing of those should be, the spacing of the bottom between the ground and the first section of the guardrail should be a minimum of 4 centimeters. And the tie barriers. The tie barriers is a topic where I believe it needs to be highlighted quite a lot, because we have seen in the past that some of them circuits that don't usually necessarily follow the instructions within the guidelines, and sometimes tire packs are not installed correctly. And I would like to remind all the circuit owners and all the SNs listening that the simulation and the studies and the research we do, and when we refer and recommend specific energy absorbing devices, we take into consideration that these elements are constructed as specified in the guidelines, and the energy dissipated if there is an impact on the tire barrier and is not connected correctly, that tire barrier will not work effectively and it will not dissipate the energy correctly. So what we recommend is to have usually about 5 or 6 packs of tire barriers installed as seen in the guidelines with a bolt and spacer, and then moved into the position where it should be placed, and then again connected appropriately to the next 6-pack or 5-pack, and all of that again connected into the first line of protection appropriately. Usually, again, for tire barriers, we can see that if ground permits, we recommend for that to be dug 5 to 10 centimeters under the ground, and that helps with then tire barriers remaining in place in case of an accident and not lifting under the car. The conveyor belt is, of course, highly recommended because it also provides an extra level of safety and it dissipates that energy, that impact energy effectively. And the inserts are usually recommended based on the CSIS or safety study. And the last, or maybe before the last, again, another set of energy absorbing devices is the TechPro. There are lots of different configurations based on the analysis that we do. So you can have it from low impact speeds to very high impact speeds. And you can see quite a few examples of them on your screen. Next bit is the high speed barrier. You can see the specifications again within the guidelines. The typical high-speed barrier is comprised of usually a 6-row tie barrier. You've got the first line of protection as your wall, could be a wall, big guardrail. The 6 rows followed by a Tech 2 barrier configuration, and that is classed as a high-speed barrier. So on areas where we expect to see very high impact speeds, this is one of our preferable options. And another type of energy absorbing device which could potentially work well usually on street circuits, on areas where space is very limited, is a safe air barrier. The safe air barrier again is typically installed on a concrete wall, which is properly solid. It has a tabular steel plate that distributes the energy into the foam. You've got the foam sections, which can be interchangeable. So depending on what impact speeds are expected on a section of the track, these foam inserts could be replaced to allow a stiffer or a softer configuration. And then you have the retention straps to anchor the steel plates between the concrete wall and the debris fence. And now, last bit for this topic is the second line of protection. As I said earlier, the second line of protection is typically the debris fence. And we have two types of debris fences. We've got the non-permanent, we call them mobile mainly, mobile debris fences, and we've got the permanent, which are installed into the ground, debris fences. What the debris fence is comprised of, you've got the reinforcing cables, you've got the 45-degree angle top section, which is typically designed to catch any debris flying perpendicular and very close to the circuit's proximity. Then you have the high tensile mesh, which from our tests shows that is capable of retaining a substantial amount of weight. And then you've got the connection between consecutive fences. It's very important that this, on a mobile type fence, these connections should always be kind of connected properly and as per the supplier's recommendations, because this is how the energy is dissipated in case of an accident, is dissipated through them. And then the stabilization structure usually goes between the end posts and the middle posts to provide extra rigidity into the structure itself. And that was myself, and I will give the floor to Tom.
Stavros, thank you. Thank you very much. That was fascinating. A few questions have come in. We're going to get through a few, Nicola, then we'll come to you. Actually, first, can I say a lot of you are commenting saying you want to watch this again. Panic not. It will be available from tomorrow on the platform. Okay, so the opportunity to see this and all the other seminars we've got this week will be made available. But Stavros, a few questions come in. Start with the CSAS system. This is from Sapir from Singapore. Hello again, Sapir. Do we use CSAS for street circuits? If yes, how do we communicate the modelling output to the ASN? And if not, what other methods do we use?
Thank you very much for the question, Sophia. So we use the CSS for every single circuit. It can be street circuit, it can be permanent circuit, it can be anywhere. We use that software for any circuit. Now, the modeling information we do not share with anyone or the ASN apart from the inspector, because this data is confidential and it remains with us. What we do, as I mentioned earlier, we do recommend and create a report for the ASN, which contains all the recommendations. And that recommendation is created. These recommendations are created based on the information that we have had from the safety study, from the CSIS tool. It's based on the communication that we had with the inspector himself, and they are compiled into a plan such as what I showed earlier. And this is typically the information we provide to the ASN for them to distribute to the circuits and for the modifications to occur. So basically, to answer very quickly. We do not, unfortunately, provide the CSIS data to anyone apart from internally.
Okay, I think you've just answered Matt Balcom's question. Hi, Matt. Is there an opportunity for an ASN race director to gain access to CSAS reports for circuits they are responsible for?
Unless they are working with us as circuit inspectors, I don't think so, no.
Okay, look, let's just a couple more very quickly. Kevin Glass. Hi, Kevin. Are the limitations of each grade available? For example, the maximum speed. Regional, national level racing is starting to see bigger, faster and more modern vehicles. For example, the difference between a 1996 BMW M3 and a 2022 GT3 car, for example.
So, yeah, I mean, the modeling and stuff, because it depends on how you use the data. You could usually, even without having a CSIS software, you could fairly quickly extract a speed profile from a specific circuit. Let's say you've got a circuit that you've been using for so many years, and you can take a speed trace from back on the 1996 and a speed trace to now. And that could fairly easily give you confidence as to how much the performance levels, first of all, have increased and what roughly to expect in case of an incident. So we kind of do and use the CSIS tool mainly because we don't have necessarily all the physical data in play, and we're also trying to use it as a prediction tool moving forward. So as I said, we can use for ourselves, we can use that data, we can predict and create a vehicle model that is equivalent to, let's say, a GT car to replicate these performance levels and predict potential incidents. But if someone wanted, someone who doesn't have such a tool, they could easily do an analysis themselves by comparing speed traces. I hope that answered and didn't confuse the matters more.
Stavros, thank you. Look, just final one actually from me, but a lot of circuits these days are, of course, running car races and motorbike races. Does the CSAS system simulate motorbike accidents?
That is, yeah, so it's going to be a long conversation. But
oh, no, we haven't got time for a long one.
No,
is there an easy answer to this, or should we move on?
It doesn't. But we are closely working with FIA FIM to understand their soft simulation to capabilities and get a bit more understanding when we do our analysis. And we have some escape lines. We do work with them closely to get a bit more understanding of what to expect in case of a motorbike incident. But we do not calculate a motorbike incidents, no, unfortunately we do not. But we have that close communication with FIM to get more understanding.
Thank you, Stavros. That's fantastic. One thing that's become apparent this week is none of our sessions are long enough, but we have so much to get through. And I'd now like to welcome back the busiest man in Geneva this week, Nicola Danesi, FIA Competition Safety Engineer. We've seen you already today, this morning. But talk us through circuit equipment homologation, please.
Thanks again, Tom, and welcome again to everybody. So I will present quickly this part of circuit equipment homologation, which is strictly related with what Liz and Stavros were saying before. In fact, once we have the homologation of the circuit specifically for grade 1 and grade 2 generally, we can also have, let's say, a background of some individual homologation that are very similar to what we were explaining this morning. So the homologation of the equipment itself, that is not the circuit, but the surrounding and the tools that are used to prevent some kind of situation. So starting from the debris fence, for example, there is a standard dedicated to the debris fence which defines all the parameters and the performance to make sure that these debris fence are able to withstand all the incident situation to give the best protection as possible to the spectators. And in fact, now I will briefly show you a video of what is a test that normally we consider the homologation. As you can see, is a test in scale 1:1, and is a vehicle with the mass over 1,000 kilo sent with an angle to at 120 kilometer speed. So a tough test, but it can define precisely what are the possibilities and the performance that are capable these devices. For what concern, again, labeling and holograms, also this device, as you can see in the picture on the top part of the slide, present a label and a hologram to certify the homologation of each section of the device. Going now to the second point, the circuit light panels. The standard of reference is the 3504 from 2019. And the light panels, they must ensure a minimum luminance to be able to be seen by the competitors in all the conditions of weather. Therefore, is an important level of luminosity to give all the information from the marshalling for what concerns the flags and all the information that are needed during the race event. In the technical list, which is the number 81, we have three different parts, part 1, 2 and 3 in relation to grade 1, 2 and 3 panels. The regulation, I will just state it for the part 1, which then is translated with the different section. So basically the grade 1 panels are mandatory for all the existing grade 1 circuit which are hosting a round of FIA Formula 1 World Championship and for all the new grade 1 circuit. On the other side, they are only recommended for the grade 1 circuit which are already homologated, previously homologated. And this is the same also for the other categories which are stated clearly here. For what concerns the circuit light panels, there is also a guidelines in terms of installation and best practice. In fact, we must ensure the visibility, the maximum visibility of this tool, because they are at the end a way to communicate information to the drivers and the competitors, and therefore must be visible. The second way, for example, in the guidelines are explaining certain information, for example, that the panel must be installed at least 50 meters before the braking point of each turn. And on the other side, there are also some suggestions in terms of safety, because these panels must be installed, of course, in a safe area, so they should never be installed on parts of the circuit that are moving or barriers that may shake during some situation. On the second hand, of course, there is a complicated regulation in terms of installation and cable and wiring. For that, we send the competitor and the circuit manager back to the guidelines that are done by the manufacturer of the circuit light panels. I will go now to the pre-last point of this slide, that is the paints for motor racing circuit. The standard of reference is 3503 from 2019. And the scope of the painting is, of course, to give some performance requirement to the asphalt in certain conditions, for example, such as rain or a specific situation. Otherwise, they must be very visible, and they also need to present a luminance coefficient and some chromaticity and skid resistance in wet condition. The technical list of reference is the 78, and since 2021, the usage of the homologated paints are mandatory in all the FIA license circuit. For what concerns the environment as well, we have a note on this topic that is very important, because all this paint must be only water-based to prevent any kind of additional pollution in terms of water or the surrounding of the circuit area. Going now to the last point is the reference to what also Stavros was explaining before, which are the circuit barriers. Differently from the debris fences, the circuit barriers are active strictly and really to try to decelerate and reduce the impact intensity for the drivers. Meanwhile, the debris fences are more designed with the idea to protect spectators and marshals. Therefore, circuit barriers, the only objective is to dissipate energy. How do they do that? By the design, how they are made. For example, here we have some examples that are stated in a technical list for some configuration. And the material itself, inside these barriers, there is a specific kind of foam. This foam helps to dissipate energy, and also the wiring, the way these blocks are kept together, is a specific way to dissipate energy. Now, if the video will start, you will see this is an homologation test with, of course, is a slow motion. But you can see a sled with an important mass that is going through the barriers, and you can see how is the deformation of the barriers, and the barriers, of course, are connected, and this connection and the nature itself of the barrier transform the energy from the sled and dissipate it in the safest way possible to reduce the G's to which the driver is exposed. And that's it.
Nicola, well done. That was excellent. Just on the topic of paint, for use in the runoff area, in terms of performance, abrasive paint versus gravel, I just wanted your thoughts on that in terms of the effectiveness of slowing down.
Yeah, of course. Well, certainly in terms of slowing down, the gravel may be more effective, but we need to keep in mind that circuit, they may have different objectives in terms of hosting events, and as Liz and Stavros were explaining before, there is a lot of things to take into consideration. But for sure, the paint is one of the solution that we like to take. They increase a bit the terms of friction compared to the one that the asphalt can offer, especially in some condition, and also can allow vehicle to safely come back to the race in case there is not an incident.
Great. Thank you very much for that. Just before we stop for a quick break, Stavros, are you still with us?
I am indeed.
Only that Paul Trafford, hi Paul, good to have you with us, has come up with a very interesting question. When a circuit is graded and inspected, at what stage is a medical inspection of the medical centre done by a doctor and not a circuit inspector?
That is a very good question. So for the medical inspection stuff, so that is slightly different process from us. We have the medical manager, which when we receive the dossier for a circuit, they provide us with the plans for the medical center. They provide us with the plans for access and egress and the time needed to get to the nearest hospital. So these plans are sent from ourselves, from the circuit safety team, to the medical manager, which he is responsible to approve or not. And there is a direct communication between the medical team, the FIA medical team, with CMO, Chief Medical Officer of the circuit, and there is that direct communication between them to understand if there is any further changes needed before the approval happens. But if, let's say, for example, if you got a homologation, a dossier, which you have added all the information we need, as I said, the medical center, all the lead times, the medical questionnaire, and we forward those information to medical manager, which is then in communication with the CMO. If, first of all, he is happy with everything that he has received, he approves that in principle, and then the last check is done when things are finalized. But the specific times, I guess, is mainly between because it's, I guess, the CMO who approves the medical center itself and the medical facilities of the circuit.
Brilliant. Stavros, thank you. I've got a quick one for you, actually. Nicola, before you go, I'm not letting you go just yet, but night racing.
Yes.
On the subject, I'm going to ask this to Nicola. What is the minimum lumens for track lights, circuit lights at night?
For that, I think maybe Stavros is the best person to answer that, because it's not really included in the homologation.
I think is, if I'm not mistaken, is above the 240 lux. I'm just going to double check because I've been working with both the karting and the main circuits, and there is a different value. But on top of my head, I cannot give you a value and being wrong online. But I think it's above 200 lux. But it's basically specified within our guidelines. Okay. You see, we've got a specific number in there. A minimum that needs to be, and that kind of minimum is when you do a light study on the circuit. At any point on the circuit, they provide us with a report of that value is continuously supplied into the track surface. But the minimum value, I think I'll have to look it up myself.
All right, but 240. All right, let's have a quick break.